and I should probably say what the algebraic mapping cone of a chain contraction is. This is just the chain complex version of the topological mapping cone. The idea, like with the topological mapping cone, where you've got, say, some space X mapping into Y, you take the mapping cylinder and then you cone off on X. So this is saying that the image of X is trivial in Y. The same is going on with chain complexes. The algebraic mapping cone is taking well, roughly speaking, it's just do this very quickly. You're taking the direct sum of C and D with a shift, and you have boundary maps such that the image of F is trivial in this product, within this sum. So it's the chain complex version of this. Secondly, so now going to spaces, the torsion of homotopy equivalence now if we have finite CW complexes.
Sorry, should that say the torsion of a chain equivalence?
Yes. Oh, yeah. Getting ahead of myself. Now if you have a homotopy equivalence of finite CW complexes, this induces a chain equivalence, and then we take the torsion as above of the chain equivalence. Yeah, that's how I want to write that. And then, yeah, you take the mapping cone, the algebraic one, and this will be in the Whitehead group of pi 1 of X. This allows us to define the notion of a simple homotopy equivalence. And I'll spend the second half of the lecture trying to explain what this means geometrically. We say that a homotopy equivalence is simple if it has zero torsion. So this is, wow, f from x to y. Okay, so let's return to thinking about s-cobordism. So all these boundary matrices, delta k, be diagonalized to leave plus or minus group elements down the diagonal. So this is plus or minus G1 if and only if the torsion of the inclusion of M into W is 0. We've kind of more or less already explained this in the setup. And then I should define what an s-cobordism is. Well, an s-cobordism, S for simple homotopy equivalence, s-cobordism is an h-cobordism with trivial torsion. So if we have trivial torsion, we can diagonalize and get group elements down the diagonal. Then we can change orientations and change lifts of our handles and get the identity down the diagonal. Then if the dimension is high enough, we can use the Whitney trick to realize these algebraic intersections geometrically as single points, and then this allows us to geometrically cancel the handles and get a product cobordism. And so writing this all down gives us the s-cobordism theorem. So if we start with an s-cobordism between m-dimensional manifolds for m greater than or equal to 5, then W is diffeomorphic to a product. Restricting to the identity on M, and hence M is diffeomorphic to M. And so we saw that the Whitehead torsion of an h-cobordism is an obstruction to it being a product, and in fact all possible Whitehead torsions can be realized by a cobordism with that torsion, which is not a product. So we have a proposition saying they can all be realized. So if we have a closed m greater or equal to 5 dimensional manifold where the fundamental group is pi, say, then for all elements of the Whitehead group of pi, there exists an h-cobordism from M to another, to an M prime, such that the torsion of this h-cobordism is our element tau in the Whitehead group. And this is in Andrew's book. This is 8.22 in Andrew's book. Okay, we'll take a break here, and I'll talk about what simple homotopy equivalence means more geometrically after the break.